functions of more than one variable, most commonly 2 or 3 variables. And this is referring to the inputs. People typically think of this as being kind of the main topic of multivariable calculus. It's the reason for the name, multivariable calculus. What are we going to do with these functions? Well, what we always do in calculus, ultimately differentiate them and integrate them. Okay, but being in higher dimensions, it is harder to understand. It definitely still takes a lot of work. So our first unit is really vector valued functions of a single variable t. This middle unit is the main part of the class. Functions of more than one variable, more than one input, but a single output. The last part of the class, which is probably the hardest part of the class, is about what are called vector fields, where you got more than one input and you got more than one output, or you've got a vector valued output. I'm going to use a notation that the book doesn't use, but I think is worth you getting used to. The general context that we want to talk about is a function f that takes, in general, actually, 2 or 3 or 4 or n inputs, whose domain is a subset of Rn, n-dimensional space. Most commonly, n is 2 or 3, and whose outputs are real numbers. Inputs are n-dimensional, typically thought of as points rather than as vectors. Outputs are numbers. Real numbers. R, this funny looking R, stands for the real numbers. The Rn stands for n-dimensional points whose coordinates are real numbers. Most commonly, n equals 2 or 3. Almost always, you could probably say as well. Will we ever consider something bigger than 3? I might. But the books, certainly the book's main emphasis is n equals 2 or 3. As an example, z equals f of xy is, let's pick a linear function. 2x minus 3y plus 4. A linear function of 2 variables. Actually, those who took 50Q with linear would say this is not a linear function because you're not allowed to add a constant. But in this class, we're not doing linear algebra, and so we allow ourselves to add constants. Before we think about trying to understand the graph of this function, how to understand the function graphically, we should think about domain and range. The domain is the set of all possible inputs. That's always assumed to be the biggest possible set of R2 in this case, 2-dimensional space, that we are allowed to plug numbers into this function for. So that means you want to avoid dividing by 0, and you also want to avoid taking square roots of negative numbers because we're not going to do imaginary numbers. Hey, this is a simple enough function that we never divide by 0, and we never take a square root of a negative number. So the domain is the entire plane R2. All possible ordered pairs forms the domain of this. The range is the set of all possible outputs. Is it possible to get every number as a possible output? I hope it's pretty clear in looking at this and thinking a little bit that yes, it is. Any number z is a possible output. one way you could see that is you could say, well, let's just pretend y is 0, so this term goes away. The resulting expression 2x plus 4 can reach any value of z by changing x. For example, if I want to reach z equals 8, I choose x equal to 2. If I wanted to get an output of z equal to 10, I'd pick x equal to 3. If you allow for other values of y, then x can be something different. You're still going to get any possible number out for z. The range is, in fact, all of R. Any number is a possible output. If you wanted to give a reason for that, you could say, for any given z, let's see if I can do this calculation in my head, set y equal to 0 and set x equal to z minus 4 over 2, and you'll get z out. What did I do there? I looked at that equation, I set y equal to 0 and got z equal to 2x plus 4, and I solved for x. Subtract 4 and divide by 2. If you replace x with that and replace z with 0 and simplify, it simplifies to z. Okay, that was a calculation I did in my head. In general, it could be very difficult to do that kind of thing in your head. But that would be a brief reason why the range is all possible real numbers. Give me any real number, what's an example of an input that gets mapped to it under this function when you plug that input in. What's the graph of this look like? The graph of f. Well, what is the graph? What does it even mean? What's an ordinary graph that you've always made? You've let x vary and you made values of y, you plotted points and connected the dots. We could do likewise here. We could let x and y vary, maybe make a big chart, x values across the top, y values along the side, outputs in the middle. Be kind of time consuming. Make a big chart of outputs and plot points. Maybe you want to plot hundreds or thousands of points. I want Mathematica to do it. Connect those points somehow? With what? A bunch of lines? No, with a smooth surface. And because it's a linear function, that surface will actually be a plane. But in general, you should know the definition of the graph of f as the set of all three-dimensional points, x, y, z, typically assumed to be rectangular coordinates, where z equals f of x, y. That's what the graph technically is, and you should know this definition. You could also describe this as the set of all x, y, f of x, y, as x and y as a point varies over the domain. Varies over the domain in the plane R2. Which in general might not be all of R2. Might not be the entire plane. The next example, it won't be. You should know this. But yeah, you'd have to plot a bunch of points, somehow connect those points with some smooth surface. Doesn't sound like a pleasant job. Technology can do it. Mathematica can do it. In Mathematica, first of all, if you want to define this function, do it with two inputs like this. F of x comma y. They're both variables. This function was 2x minus 3y plus 4. To see the true graph of this function, use plot 3D. Type in the function name, let x and y vary over some range of values. The graph is a plane. Shouldn't be too surprising because it's a linear function. Where is the XY plane in this picture? I could put it in there by also graphing the function 0. That'll graph the XY plane. That's the blue plane. So the function that I'm interested in is this orangish graph. Sometimes it's above the XY plane and sometimes it's below. The z-axis goes up and down, positive upward. Mathematica's default, I'll remind you, is to make the positive x-axis go to the right and the positive y-axis go into the screen, away from you. That's Mathematica's default. So in general, think with me here, this graph, it goes up, gets higher as x increases and y decreases as you move toward you here. That's when this function's increasing, which makes sense if you think about its formula. The coefficient of x is positive and the coefficient of y is negative. So it should make intuitive sense that the function values go up as x gets bigger and y gets smaller. Another way to visualize this function is with contour plot. What does this show? This shows a two-dimensional picture, actually, of what are called the level curves of the function. And if you hover over these lines, you see some numbers. That's a 0. It's kind of small. This one says 5. This one says 10, I think. 10, yep, there's a 10. 15. 15 there. 20. Go back up this way, -5. -10, -15. Lighter shading corresponds to higher outputs. Darker shading corresponds to lower outputs. Higher, you're going off to heaven. Darker, you're going down to hell. Okay, you could think of it that way if you wanted to. Head toward the light. You want to go to heaven. What is this really showing you? It's showing you the curves, in this case, lines of intersection with different horizontal planes with that original graph. The output of 0 is where that original graph crosses the XY plane, in fact. If we get rid of the frame arrow false, and add in axes, and don't make the R uppercase, we can see axes in here. We see that this line where the output is 0 is not through the origin. Looks like it's x, the y-intercept might be 1.5 or something. Is there a way to confirm what lines we get symbolically here? This example, once again, f of x is this function, 2x minus 3y plus 4. If I set this function f of xy, which is again 2x minus 3y plus 4 equal to a constant c, where c is unspecified, I can figure out what curve in the xy plane has this graph. And that'll be one of those level curves that we saw. Solve this for y as a function of x. Negative 3y would be negative 2x minus plus c minus 4. Y would be, divide everything by 3, negative 3, excuse me, positive 2/3 x plus 4 minus c over 3. So for any given value of c, I can draw this line in the plane, and that corresponds to the level curve for that value of c. So if c is 0, for example, it's the line y equals 2/3 x plus 4/3. The y-intercept is not 1.5 like I thought initially. It's actually 4/3. and the slope is positive 2/3. That's 4/3 there. That's negative 8/3 there. Slope of this line is 2/3. No, that's not negative 8/3. That's a negative 2. Slope of this line is 2/3. This corresponds to an output of 0. You could say C equals 0, but it's probably better to label it Z equals 0. What about the output C equals 5? If C equals 5, replace C with 5 there, you get the equation y equals 2/3 x. 4 minus 5 is negative 1, minus 1/3. Line with a slope of 2/3 and a y-intercept of 1/3, parallel to the original line there, which is what we saw in Mathematica. That corresponds to an output Z equals 5. Don't let it bother you that here I wrote C equals 5 and here I'm writing Z equals 5. I wrote C here because I was thinking of it as being a constant output. But yes, that output is a Z value. It's a vertical value on the original three-dimensional graph, the surface. And I can do this for other values of Z as well. Because these lines are equally spaced for equally spaced values of Z, like 0, 5, 10, 15, etc., that's reflecting the fact that this graph, the three-dimensional graph, is a plane. And yes, when I cross it with the XY plane where Z is 0, this line of intersection that you see there is the same as this line right here, with a slope of 2/3 and a y-intercept of 4/3. There's your one where Z is 5 with the slope of 2/3 and a y-intercept of negative 1/3. This one's got a y-intercept of negative 2 when Z is 10. Okay, so you should be able to do this kind of analysis. This is the simplest kind of case. Let's do a more complicated case now. I'll do a modification of one of the book's main examples. Z equals f of xy equals square root of 1 minus, let's make it x squared over 25 minus y squared over 36. First of all, what's the domain? So this is a function that is taking two-dimensional inputs in the plane R2, xy, typically assumed to be rectangular coordinates. Though to tell you the truth, there's nothing stopping you from treating these as polar coordinates if you wanted to, an r and a theta, but that's for later in the course. The output is a real number. We want to avoid taking square roots of negative numbers here. We don't want to any imaginary numbers for the most part in this course. Maybe I'll talk about them a little bit later, but for the most part, we're avoiding imaginary numbers. The domain is the set of all points xy such that f of xy is a real number, not an imaginary number, not a complex number, which is like something like 2 plus 3i, where I is the imaginary unit. And we're not dividing by 0 either. So because we have the square root here, this is the set of all points xy where the thing inside the square root is greater than or equal to 0. What kind of region is this? It's some region in the plane. What kind of region is it? Think about its boundary. The boundary of the domain is where 1 minus x squared over 25 minus y squared over 36 equals 0. What does the graph of this equation look like? If you rearrange this equation to look like this, x minus 5, x over 5 squared plus y over 6 squared equals 1, which you can do. And if you remember well enough your pre-calculus content, if you talked about ellipses and hyperbolas, you'll maybe remember the graph of this is an ellipse with x-intercepts at plus or minus 5 and y-intercepts at plus or minus 6. So the boundary of this is an ellipse. It's an oval, almost circular looking, but slightly elongated in the vertical direction. That's an ellipse. For what values of x and y is this thing strictly positive? Well, take a test point like the origin. If you plug in x equals 0 and y equals 0, you definitely get something strictly positive here. It's inside the ellipse. That's the domain. That's the domain of f. What's the range? Again, remember the range is the set of all possible outputs. What kind of real numbers can you get out of here if you plug in different values of x and y? Certainly can't get any negative numbers. By definition, the square root here is taken to be the non-negative square root, greater than or equal to 0. Also, if you think about it, there's no way you're going to get, if x and y are real numbers, you're never going to get something bigger than the square root of 1 here. Never bigger than 1. The range, the possible outputs, are all numbers between 0 and 1, and nothing else. The range is all z values between 0 and 1. You could write that with the set builder notation like this. More commonly, you'll see it written in interval notation like this. The closed interval from 0 to 1 is what that notation means, including the endpoints. What's the graph look like? I hope you can guess. When you're on the boundary, this ellipse, where this is true, the output is the square root of 0 is 0. And at the origin, the output is as high as it's going to get, 1. There's a maximum value at the origin. It's got to be some sort of upside down bowl shape. Or maybe if you take a football and cut it around its equator and set it down after you cut it, 1/2 of it, maybe like that. That's got to be what the graph looks like. Square root of 1 minus x squared over 25 minus y squared over 36. Plug it in. I want to have a domain that's a bit bigger, so I include y going up from -6 to 6. There it is. Yeah, you do see it's slightly oblong there. It's not a perfect circle when you look down on it. Not really a football shape exactly, though, either. I mean, not terribly far away from one. There's the domain is everything underneath the bowl, the upside down bowl. And the range is all the possible outputs you can get vertically from 0 to 1. But it's not flat like a plane. So if I make a contour plot of this, my level curves will not be straight lines. And they will also not be equally spaced because it's not increasing at a constant rate. There they are. You can see they're closer together the closer you are to the edge of the bowl and further apart here. Why? Because when you're near the edge of the bowl, the function values increase pretty rapidly. The graph's pretty steep along the edge of the bowl. When you get near the top, it's flatter. The function values don't increase very rapidly. It's assumed here, Mathematica does take the outputs to be fixed distances apart in z value. You can see a 0.5 there with this one. Let's see, I see 1, 2, 3, 4, 5. Effectively 5 lines to get to the origin there, where the origin maybe is a single dot as a line. So I'm guessing these are 0.1 unit apart. I'm guessing this one just to the left is going to be a 0.6. Yep. Then a 0.7, 0.8, 0.9. Go backwards toward the darker regions where the function output is lower and you get lower values, but you never get below 0. By the way, you can add more contours in here, more of these level curves. You can use an option like, I think the default is maybe typically 15 level curves, though it seems like we may have 10 here. So this produces probably the same picture. But we could add more, like 20. Then we have more of them for more Z values, where the numbers there that you see are not so nice. Even 100. Yes, though then the picture is not quite as nice, I don't think. You can also specify what particular Z values you want. If instead of putting in just a single number there, you put some other numbers in curly braces, like maybe I want to put 0.25, 0.5, and 0.75. Well, maybe 0 as well. Okay, so then it plotted those for those particular Z values. Different options that you can do to make different kinds of graphs. But again, the way these are made is going back to the original 3D graph, this thing, and slicing it with horizontal slices, horizontal planes, and looking at the curve of intersection and effectively projecting that curve down into the XY plane. That's how we get these curves, which are all ellipses. Is there a way to figure out what ellipse it will be based on a given value of C? For a given value of C, if I set this equal to C, can I sort of figure out the corresponding ellipse that I get? Yeah, you can square both sides to get rid of that square root. Then you can rearrange and write it as x squared over 25 plus y squared over 25 or 36 equals 1 minus c squared. I did a few different things there to rearrange. To tell you the truth, to write this in the best standard form, you'd want a 1 on this side. In general, c is not 1. This is not 1. If c is not 0. So effectively divide everything by 1 minus c squared. Write it like this. And then probably the best way to write that is like this. Kind of a weird way to write it, but it's probably best. If we had spent some time at the beginning of the semester learning about ellipses and hyperbolas in detail in section 9.1, we could describe exactly what ellipse this is in some nice ways. But it is these different ellipses that Mathematica made. So it's a different ellipse for each different value of C. That's the point. As C varies, the ellipse changes, just like we saw in the picture. Are there some functions where the level curves you get are like hyperbolas? Like z equals f of xy. Can I think of a function where your level curves are hyperbolas? Yes, I can. Simplest example is x squared minus y squared. Another example would be negative x squared plus y squared. What does the graph of this look like? Let's change the function to the one I just wrote down, x squared minus y squared. Here's what its 3D plot looks like, along with the XY plane being plotted there. Looks like a saddle. You want to sit on it, right? Ride the horse. In fact, yeah, the origin is called a saddle point here. And if you think about this carefully, it makes good sense based on the formula. In the x direction, so to speak, for different fixed values of y, it's a graph of x squared minus a constant. Parabola looking like that. Maybe shift down as y changes from 0. And in the y direction, which goes into the screen, it's looking like an upside down parabola. Because for any fixed value of x, you've got a constant minus y squared. Combine the two, you get this surface. You can see the intersection of the surface with the xy plane where z is 0 looks like an x. One level curve is that x when z is 0. What are the other level curves? You can't necessarily tell just from looking at them, but they are hyperbolas. Lighter means higher, darker means lower. Like this hyperbola is where the output is 5. There it's 10. There it's 15. 20. -5 here. -10. -15. Just like we saw in the three-dimensional picture. The function goes up in value as, like, for example, y is 0 and x goes away from 0, and down in value when x is 0 and y goes away from 0. Where level curves are closer together, that's where the graph is steeper. They're close together up here, they're close together over here, and down there. Where they're further apart, the graph is flatter. I mean, the derivative is larger over here than it is over there. Yes, so you have to be careful what you mean when you say the word derivative. There's more than one derivative. In fact, at any point, there's infinitely many derivatives. They're called directional derivatives. It depends on what direction you go in. The rate of change depends on the direction you go in. All right, that should make some sense. If you're standing on a mountain, are you going to go directly up the mountain or down, or are you going to go along the path that's not too steep? Depends on the direction you go, how fast your elevation changes. We can also do functions of 2 variables, or 3 variables, I meant to say. Maybe, I don't remember what letter the book uses for the output. I like using u. U equals f of x, y, z equals, oh, I don't know, how about x squared plus y squared plus z squared? What's the graph of this? Mathematically, the graph is the set of all points x, y, z, u in 4-dimensional space with the property that u equals f of x, y, z. Is it possible to graph that? No. Is it possible to understand this graph that we can't imagine? Yes. Somehow. We can do calculus with it. We can do rates of change still. Partial derivatives and directional derivatives. It's somehow a 3-dimensional hypersurface sitting inside 4-dimensional space. Somehow the graph of this is a 3-dimensional hypersurface. 3-dimensional surface. Call it a hypersurface. Sitting inside 4-dimensional space. What would happen if we sliced such a hypersurface with a hyperplane, which is a flat 3-dimensional surface in 4-dimensional space, just like a regular plane is a flat 2-dimensional surface in 3-dimensional space? What would happen if we slice this with such a plane? Instead of getting level curves, we get level surfaces. And those level surfaces can be graphed with not plot 4D, but contour plot 3D. As x, y, and z all vary. What are these? They look like they're spheres. I think the default here might be 5 of them. Spell contours. Let's try 10. When you slice this 3-dimensional hypersurface sitting inside 4-dimensional space, with three-dimensional flat, quote unquote, hyperplanes, you get, and project those into three-dimensional space, you get spheres. Different spheres for different u values, different constant u values. So yeah, the graph of this equaling a positive constant is a sphere, centered at the origin with various radii for different c's. What if I change the function? How about make one of those things a minus sign? No longer spheres. What are they? They're hyperboloids. Some of one sheet, some of two sheets. I hinted at those before. Described in the reading, I believe, in section 10.1. Or was it 10.5? I'm forgetting. Another suggested reading. I said skim on Moodle. What if there's two minus signs? And then there's still hyperboloids, but different directions. Is this helpful? It can be. Because it can help you understand how the function changes. Because these are different output values. X-axis, for example, is left and right. As x goes away from 0, the function values increase. And that the formula makes that make sense. And what that means is these surfaces that you see over here on the right, first the orangish, then purple, then green, those are increasing outputs. Function values decrease as y or z go away from 0. So, for example, as you go out away from the origin here, I bet these are negative outputs. These surfaces correspond to negative outputs. What you're looking at here is a decomposition of the domain of the function. And you're thinking about how the outputs change as you move through the domain, which is three-dimensional space.